Good. Okay. Yeah. Okay. Who's excited for the zoo? Yay. I hear it's enormous. Okay. Yeah. I'm Rob Kavanagh. I'm from Astron in the Netherlands. And today I want to tell you about trying to figure out what magnetic fields are like on substellar objects. Um, why do we want to do this? I hope you don't need too much convincing, but there's a lot of reasons why, such as these. I mean, they tell us about if we can measure the magnetic fields of substellar objects, we can learn something about their interiors, we can learn about their habitability, and we can also potentially use that information to look for orbiting planets and moons and stuff like that around them. We've heard a bit about this already in this conference. So Florian gave this nice talk on Monday, I believe, um, showing just the effects of atmospheric escape on an exoplanet as a function of how strong its magnetic field strength is, right? So this is pretty obvious. And then another thing which I'm particularly interested in is geometry, more specifically, how this magnetic field is oriented relative to stellar wind coming in and obviously radiation from the star. And you can see how the escape rate of one of these atmospheric tracers varies depending on the angle the magnetic field makes with this incoming flow. Another thing which I've spent some time thinking about in the last couple of years is just how do the magnetic fields of stars facilitate the detection of exoplanets and satellites? And so in this figure from a paper from last year, we were looking at what systems are visible a lot of the time in the radio. And we found there are only certain configurations, one dependent on the inclination of the rotation axis, but also the magnetic obliquity. So this is the misalignment between the magnetic axis of the star and the spin axis. And you can see specifically here, this was something cool that came out of this was that depending on how oblique the magnetic field of the star is, well, I guess if we detect planets in the radio, it's more likely that their magnetic fields are reflective of an obliquity that looks something like this. So as I've been working on this, I've kind of come to realize that the terminology for these objects can be a bit kind of muddied sometimes. So just to make a quick clarification going forward. So, okay, we have late M dwarfs and brown dwarfs, right? And so at some point, we lose the ability to burn hydrogen in these objects. And so these are normally called ultra-cool dwarfs. But then substellar objects are brown dwarfs and exoplanets. So just bear that in mind, right? And so, sometimes, so I'm going to talk about brown dwarfs, but I mean, people refer to them as either or. So how do we measure magnetic fields? This is an important thing to figure out. Okay, we've heard a ton about the Zeeman effect, right? We measured the splitting or broadening of spectral lines in the presence of a magnetic field. This is run-of-the-mill stuff for solar-like main sequence stars. But I'm glad that this was shown and that it's not something I am an expert in, but I mean, you can see very clearly here as we go to lower and lower effective temperatures, and the spectra of these objects become absolutely contaminated by these molecular lines. So trying to model this is a real pain as far as I understand. And also these objects become fainter and fainter, right? So the Zeeman effect is out as far as I'm concerned right now for these objects. But what if I told you there was another way? And it's radio emission. And so this is the kind of picture that I want you to start thinking about. And it relates to electrons circulating in magnetic fields and producing radio emission. And the main important thing is the fact that the frequency that you observe at tells you exactly the magnetic field strength as to where that emission is coming from. And Sana talked a bit about this earlier. Am I? So, okay, a little bit more detail about this. So this type of radio emission, more specifically, it's electron cyclotron maser emission, is generated due to electrons being accelerated along magnetic field lines, right? So we need to inject or accelerate electrons somewhere down here in the magnetic field of whatever this object is. Some of these reflect, and this is when you get this electron cyclotron maser coming online, so to speak. And so this emission is beamed out in a hollow cone shape. So immediately you can see that there is a geometric effect here. That means, if you look straight into that cone, you won't see the emission. You have to be at the right angle looking down onto this magnetic field line to see this. So for ultra cool dwarfs, this is our kind of picture of what their radio emission actually looks like. And so these were first detected about 20 years ago. Normally what you'll see this quiescent noisy emission, which generally is not resolvable in terms of any structure. And then you sometimes also see these periodic bursts that we think are occurring at the rotation period of these objects. And so the accepted picture of this now is something that looks like this. We have an object with a large-scale magnetosphere that's filled with plasma. What is filling it with plasma? We still don't know. There are lots of options. And they're actually the manifestation of this quiescent and bursting radio emission comes from two different processes, we think. Again, this is all based on what we see in Jupiter. So this quiescent emission is thought to come from a radiation belt. And so these are relativistic electrons trapped in the magnetosphere producing synchrotron emission, whereas these bursts are thought to be due to coherent radio emission, the electron cyclotron maser. And you can see some nice examples of the first ones of these objects being resolved actually in the radio. And so I'm not going to talk about synchrotron emission. I'll throw that hot potato to Joanne, who's going to talk tomorrow more about this. And so, yeah, just very quickly to make the point on what this radio emission can give us. So recently, Sana did this really nice work looking at the star AUMIC, which hopefully everybody knows. And more specifically, we were looking at how the radio emission is modulated as a function of rotation phase. And over like the course of a year, we see this consistent pattern where it bursts positively and then later on negatively. And we were trying to figure out why this is. This was our simple approach to this issue or challenge, I guess. We looked at Jupiter, and it has this auroral ring, right? And so we made a simple geometric model involving lots of angles and radio emission being beamed from a ring shape on the poles. And this is something that we didn't actually make a big point out of, which is actually very cool in the paper. It was just the fact that, okay, this is the magnetic field topology from ZDI during the same time of the radio observations. This is what we inferred from the radio. So it's actually very consistent, even with this simple model. So that is nice. Onto the actual object that I want to talk about in 2 minutes, apparently. Okay, this is, you might remember, the typical light curve of an ultra-cool dwarf. But the object that I've been interested in for the last while looks something more like this. This is very strange. Okay, and so like, what is going on here? So this is from a T8 dwarf called blah blah blah, phone number J0623. It's the coldest brown dwarf ever detected in the radio to date. It's so cold, it's actually the temperature of a pizza oven, as I've been told by Kobe. So if you want to know what it's like, you can stick your hand in. No, don't do that. So we saw this light curve, and I was thinking, okay, well, what is going on here? Can I do something similar for like an auroral ring? Short answer is no, it doesn't work because it gives you symmetric profiles, and you saw there's lots of asymmetry in that light curve. What I found that does work is if I just allow a little subset of the magnetic field lines in this magnetosphere turn on, so to speak. And so if I do that, I can actually reproduce the shape of this quite well. So this is still work in progress. Lots of corner plots are being assessed in 10 dimensions. It's a nightmare. And yeah, finally, I made this earlier. I thought this was interesting. kind of thinking a bit more about like what is going on in the dynamo in this object. If we look at the dipolar field strength and obliquity of its field and compare it to M dwarfs and the solar system planets, can we say something about its interior? I'm not like a dynamo expert at all. Maybe there's someone in the room who has some insights. That'd be nice to hear about. I'll leave you with some concluding thoughts. Something that we can potentially do with this method is maybe trace magnetic cycles on these objects if they have them. Obviously, open question, why are these field lines activated? I mean, one option that I was thinking about was like maybe prominences. I mean, that's very hand wavy. Also satellites, this is a natural option. We need lots more data to figure this out. But yeah, that's it. Happy to take questions. Well, do you have complementary information on the location of the objects? No. I wish. So, I mean, yeah, that is an interesting thing. Oh, sorry. The question was, do we have complementary information on the rotation period of the brown dwarf? And the answer was no. Maybe you can do it. Okay, so the question was, do I expect the polarization of the emission to change? And then, sorry, I missed the last part. It was about UV. Oh, the variability. Yeah, so this is an interesting thing. So we have wide-ish band radio observations. They go from like a gigahertz to 1.5 gigahertz. And so, I mean, with the fit for the light curve, we can say, okay, what would this look like at different frequencies? And at different frequencies, if we assume the configuration stays the same, you start to see different polarizations coming in. So it's all left-handed circularly polarized, but you see right-handed circularly polarized emission come in as well at lower frequencies. We don't have any evidence for any changes in the variability, but we haven't gotten any additional data yet, so we don't know. I'm hope it would be very cool if it did change, because that could highlight that, okay, either where these field lines are appearing has changed, or maybe the magnetic field, the large scale magnetic field, has actually evolved over the course of a year, something like that.
Okay, great. And thanks, Rob, again.